close it was to.
I made a bad deep fake of
They're full of eggs.
Yeah, and right now they're not even good, but they'll be good soon. It'll be very difficult to tell the difference.
Like the computer generating a face out of like other people's faces.
Oh yeah.
And then they mess up every once in a while.
Like the Princess Leia.
Because you'll like see like teeth. Like right here, just like
Her
upper
face.
teeth. It's like,
That looked totally fake. You can tell.
That was Uncanny Valley right there. Yeah, that movie. Have I talked to you guys about Uncanny Valley? I think I have. Well, so yeah, with the snack, crackle, and pop. So Uncanny Valley is this idea that so suppose who's seen Blade Runner? I know Colin has. Okay, so Blade Runner is this movie where androids, like robots basically, are indistinguishable from a real person. Like I could be an android, you have no way of knowing. Okay. So obviously, if you can make a perfect replica of a human being, robot, for example, then that's not going to weird you out because you literally can't tell the difference. And then also, if I made you like a robot that was just clearly fake, like obviously not real, that wouldn't weird you out either. You'd be like, oh, it's just a robot. But there's something in between called the uncanny valley, where there's like an uncanny similarity, like they look almost human, they sound almost human, but you just know it's just weird and it's off-putting. That was on the cusp of like the CGI they did for her in that movie was like very good, but it's still, you're like, something's off. Yeah. Your brain just picks up. You guys have seen that robot, right? What's her name?
The one Will Smith.
Yeah, it's like this. It's an AI robot.
Yeah, she's creepy, man.
Sophia.
That's
This I would say is here. I'll show it to you. This is still
too close.
I'm not sure if this is necessarily in the Uncanny Valley because she doesn't really look. I know it's okay. Sorry, this is Uncanny Valley. They gave her this really weirdly human-looking appearance.
And an artificial intelligent robot who wants to help change the world for the better.
I'm Steve Kovac, I'm a senior correspondent at Business Insider, and I'm here with Sophia. So, and so
Here, just doesn't get it.
the world's first robot citizen. So,
We're watching this robot. You can look it up on YouTube if you want. Sophia, the AI.
I love my human and patriots. I want to embody all the best things about like taking care of it, and to learn how to be compassionate to all things.
You get the idea. That would be like you're in the Uncanny Valley and like where you're like. I mean, imagine that she just looked a little bit better cosmetically and looked a little bit even more human, or say sounded more human. That'd be really weird. You'd be like, yeah. So okay, let's get into these forces here. So, all right, physics time. Forces. So a force is a really simple idea. It's a push or a pull. Okay. We'll get into a more precise definition later. I'll just tell it to you right now, actually. A force is anything that will cause an object to accelerate. Okay, so this water bottle has a velocity of 0. If I exert a force on it, it speeds up. Okay, so I might as well just give you the definition right now. We'll get into this later in more detail, but a force is equal to mass times acceleration. It's a very simple definition. This is like Newton's second law. So force equals mass times acceleration. F equals m. This is probably the most often used formula in physics. I'll give you a really simple example. So let's say when I push that water bottle. I don't know. Let's say the water bottle was 2 kilograms. It's probably not, but say it is. Say the water bottle was 2 kilograms, and when I pushed it, it accelerated at 3 meters per second squared. What's the force going to be? 6. Well, 6 watts. Well, what the units would be? Yeah. Yep, Trenton got it. The units would be kilograms times meters per second squared. Right? Because if you multiply kilograms times meters over second squared, what you have is kilograms times meters over second squared. Now what we do is we lump that into a unit called the Newton. You say that it would be 6 newtons of force. There's a unit of force that you're all very familiar with called the pound. That's related to gravity. We'll talk about that later. But so obviously, when the Earth pulls down on you, the Earth exerts force on. Like when I drop something, what makes this thing go from 0 velocity up to not 0 velocity? Well, there must have been a force, right? Force equals mass times acceleration. All right. So, does that make sense? Is this kind of an intro? In fact, let's hash it out actually. So when I drop something, right? So I drop a ball, okay? When I drop a ball. All right, so what is exerting a force on that ball after I've dropped it? So it's already out of my, just gravity, right? We know how fast it's accelerating, don't we? What letter do we usually use? Usually it's that letter G, right? So this thing has a mass of m, okay? The mass is m. We know that the acceleration
Times 10 because you're trying to equates to how much.
well, g times t would give you the speed after some amount of time t, right? But I'm just saying the acceleration itself is g, which we know is 9.8. So therefore, I mean, if this equation is true, which it is, they didn't lie to you, then the force due to gravity, how much gravity force is there exerted on this object? Well, mg. That's a big formula right there, mg.
I like these kind of things.
Let's do a concrete example, very simple example. Suppose for a second that I'm holding a rock. Here, another great hand drawing. Okay, make it up. There, it's a rock now. Okay, this rock is, let's say, 5 kilograms. Now I'm holding that rock here. Here's the rock. It's a pretty neat toy, isn't it? Yellow. Blue. Yellow. Blue. Anyway, I'm holding it. All right. So gravity must be pulling down on him, right? Now, how do I calculate that? Well, the force from gravity, the force that Earth pulls down on him, is mass times g. So this would be, mg would be 5 kilograms. Put the units in. 5 kilograms times 9.8 meters per second squared. This would actually be, exactly 49 newtons. How do you feel about that?
Good.
All right, now someone take a shot in the dark here. If that was the only force, what would this thing be doing?
It would go.
It would be accelerating, right? If there's a force on something, then it accelerates. Okay, so, but it's not. So what's my hand is exerting a force to oppose that. There's some notation back from geometry class where I say those are equal to each other. The force exerted by my hand in the upward direction must also be 49 newtons to balance it out. So I need to modify this a little bit. So it's not quite as simple as to say if there's a force, there's an acceleration. What I have to talk about is the net force. The net force. So you guys know what I mean by the word net?
Combined.
Like combined, yes. net kind of like, you know, that looks ugly. This marker is not doing too good. You know, it's like if you spend $10 on materials, make something, sell it for $15, your net was $5. Okay? So that's probably not very good either. So F net will give you the mass times acceleration. So in this example, what was the actual acceleration happening? 0. So the net force must have been 0 for that to happen. But then I can calculate how much force did my hand have to exert. Well, then I say, well, if the hand wasn't there, well, sorry, I said that wrong. Gravity is exerting mg because that's what we know about how gravity works. And so my hand must be exerting equal opposite force. You feel okay about that? Yeah, question?
Can acceleration and force be negative?
Yeah, definitely. Yeah, so watch this. So it's not accelerating, right? I'll make it accelerate for just a brief second. So think about that moment in time, right? It was accelerating downward. How did I do that? Well, I decreased this vector for a moment in time, right? And for just a small moment when I let, because that vector is not changing. Does Earth care? No, the universe does not care about you. Doesn't care that I'm there, okay? This vector is pointing the same amount at all times, right? 4.9. So this vector decreases. Okay, great. Now my net force would be pointing down, and I would accelerate down. Thanks for the question. That's a great question. Okay, let's back up a little bit. We have the background now of this is important, and this idea of net force is important. Okay, so let's do page 1 here. Why don't you guys put an answer down for question A? We usually use a little box for our object. I should actually show you. This is the standard notation. So I always thought it'd be funny to prank my students and make like the central object of the force diagram be like a smiley face. Because then you go to university and they'd be like, why are your force diagrams? Why do they all have smiley faces? And like, I thought that was the standard. My physics teacher told me that's what everyone does in the world. It's usually just a square. Boring.
I do that anyway.
So here's the box. Yeah, you can put a smiley in. So there's the object. That represents any object. It's resting on top of a table. So I could draw the table, certainly if I wanted to. This is kind of optional. Let's draw the table just for now. So here's my object resting on top of the table. There's two things. Now, what you are talking about in a force diagram is what are the forces acting on this object? Okay? So there's two. He's resting. So if you're at rest, what is true?
Acceleration is 0.
Your acceleration is 0, right? You're not going anywhere. Your velocity is 0 and your acceleration is 0. Does that make sense? If you're resting on a table, at least. Now, that can be a little confusing because watch this. For that, when it reached its peak, it was at rest, just for a brief moment, but it was still accelerating. So be careful. But if I sit it on a table and it's just chilling there, then its acceleration is 0. So that means, okay, this thing has a massive m. So how much force is pulling it down? Anyone? Mg. This is the force due to gravity is equal to his mass times 9.8. If you were on Mars, it would be his mass times some other number, whatever it is on Mars. I don't know, I'm curious. Let's see, I'll ask the computer. Well, I'll ask my Snapchat machine. Let's see if this works. This is another good example of living in the future. What is the acceleration of gravity on the surface of Mars? It's about 3.72076 meters per second squared. So about a third, a little bit more than a third. Isn't that amazing? We can't load a Google form. We can't have reliable. I just asked this this I just asked this computer in my pocket to tell me what the acceleration due to gravity on Mars was, and it told me the answer in 1 second. Amazing. Okay. Okay, so there's the gravity. Everyone cool with that? Now, therefore, the force from the table, the force that the table exerts on the block must be equal to that. Okay? In fact, I think I'll just say this. I found this leads to some confusion. Let's just say that we could calculate this number, and yes, this would be equal to that, but let's just denote it like this. These little bars. So that's the same as that. Part B. He's in free fall after being dropped. So he's falling, so there's only one force, right? The force from gravity, which we know is mass times g. Cool beans? Less. So whatever, There's nothing that's truly frictionless in the world, but okay, you can get pretty close with an air hockey table, yeah.
What's the life-size air hockey table?
What?
If they're looking at the life-size air.
Every air hockey table is life size. Big blue moon.
You mean a hockey rink size air hockey table?
Yeah.
There you go.